Hi guys, this video today is about average rate of change. And that phrase might be a little bit familiar because we've talked about rate of change before. Let's just read through some of the information here. The average rate of change function describes the average rate at which one quantity is changing with respect to something else changing. You are already familiar with some average rate of change functions like miles per gallon or miles per hour. In general, the average rate of change function is a process that calculates the amount of change in one item divided by the corresponding amount of change in another. So, for instance, we talked about miles per gallon. Typically, what we've seen before is something like this, where if we are talking about, for instance, miles per hour, if you have a graph with miles and hours, then usually what we've seen is a straight line. That's your constant speed is miles per hour, and that is rate of change. We talk about slope, and slope is rate of change, how rise over run, that's rate of change. So that would be something that you already know about. So what's new in this section? Well, going back to the words here, using function notation, we can rewrite the average rate of change, a of x, from a to x as this equation, f of x minus f of a over x minus a. Well, as you look at that, that should look really familiar to you. Because when we talk about slope, we have y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And you can see that these two equations look a lot alike. That's true, and that's on purpose. They are average rate of change and just your basic slope or basic rate of change. The only difference is, in this unit, rather than having a constant speed of miles per hour, instead we might have something a little bit more variable. Okay, so you might have something where it looks a little bit more like this. And so you still have miles per hour, but you're not having a constant speed. And in this previous example, it was a constant speed of miles per hour. This one is a little bit more variable. It's going up, it's going down, it has, some different shapes to it. But yet we can still find the average rate of change. For instance, if we wanted to find the average rate of change from the first hour to, I don't know, let's try to go a little bit farther over here, like the fourth hour over here, then your average rate of change would be going from here to here. And we might have talked about an example like this before, which is in reality, you're going faster, slower, faster, all that stuff, but the average would be this line, the black line that I drew in there, that straight line. And for instance, if a policeman stopped you and said, you are speeding right here, you could say, oh, but my average wasn't speeding. My average was just normal. But that wouldn't matter, would it? What he wants to know is the instantaneous. But we're talking about the average rate of change. Okay, let's look at some examples. If you take any two distinct points on a curve, the slope of the line connecting the points would be the average rate of change from x1 to x sub 2. So between the first hour and the fourth hour, your average rate of change is the slope of that straight line. The little points in between, for our case, for average rate of change, aren't as important. Okay, so for an example number 1, find the average rate of change of this function over the x interval from 0 to 3. Okay, let's talk about intervals. We've been using interval notation all year long. This means from 0 to 3, it includes the 0 and it includes the 3. And so I just drew a really basic graph, but let's say this is your graph. These are supposed to be our x values. So from 0 to 3, now I don't know where 3 is because I just made this a random graph, but from like there to there, what is the average rate of change? And so once again, that average rate of change is that slope of the straight line, not the curved line, the straight line. How do we find that? Well, what we need to do is remember our equation is up here. It says f of x minus f of a on the interval from x minus a. So we can plug in, and honestly, it doesn't really matter what order we go in as long as we stay in the same order in the denominator. Remember, that was the same with the slope. If you remember when we did slope, it doesn't really matter which one's the first and which one's the second, as long as you keep the bottom to match the top. So the same thing here. Let's just find f of 0, and then we'll find f of 3, and we'll go from there. So f of 0, if we plugged in a 0 here, that would be 0 minus 4, which is negative 4. If we plug in a 3, then we get 3 squared, which is 9. 1/3 of 9 is 3. So we get 3 minus 4, and that is negative 1. So now let's go to our average rate of change function. And it says the average rate of change from x to a over x minus a. So f of 0, we can put 0 first and then 3 second. Those are the numbers that are here inside the parentheses. They're the numbers here, 0 and 3. And we have to subtract them, just like we do with slope. And then in the numerator, we're going to put in what we found for each of those. So when we plugged in 0, we got a negative 4. When we plugged in 3, we got a negative 1. And now I just need to simplify this. So when I simplify it, I get negative 3 over negative 3, which in this case, in any case, negative 3 over negative 3 is going to be 1. Now we don't know 1 what. Is it 1 mile per hour, 1 mile per gallon, 1 beat per minute? We don't know, but whatever it is matches up with the rate of change on this graph, and so it is 1. If we had a unit, we would put our units on it, but we don't know what that is. All right, let's take a look at the next one. Consider this function. What is the average rate of change over the interval negative 4 to 2? That means we need to plug in negative 4, see what we get, plug in 2, see what we get. Why don't you pause the video here and try to plug those in and see what you come up with. Okay, when you plug in a negative 4, you should have gotten negative 18. When you plug in a 2, you should have gotten negative 6. If that wasn't what you got as an answer, you might go back and double check your signs. Because negative 4 squared is a positive 16, but there's another negative in front, so that gives us a negative 16. Same thing here. 2 squared is 4, but there's a negative in front, so that's negative 4. So that's where I'm getting my negatives from. Okay, those two are the ones that go on the numerator. Negative 18 and negative 6 go on the numerator. And in the denominator go the negative 4 and the positive 2. So negative 18 minus negative 6 is negative 12. Negative 4 minus 2 is negative 6. And so my average rate of change is 2. 2 what? I don't know. Like I said, 2 miles per gallon, 2 kilometers per second, who knows, but it's 2. In this next example, we're given a graph. And if we're able to make sense of it on the graph, then we could do that. And so if you look at the graph, it's a little bit hard to read this graph, but I think I can see that at negative 1, the graph goes up to 4. And at positive 2, the graph goes up to 4 also. We've been talking about how the average rate of change is the slope of the line that connects those 2 points. And if this one goes up to 4 and this one goes up to 4, then what is the slope of that line? It's a flat line, and the slope of a horizontal line is 0. So the average rate of change of this should be 0. And so we can just say that A of x, that means the average rate of change, is 0. If we wanted to work it out or we couldn't see it or whatever, we could plug those numbers into this function. And so if we plug them into the function, we would plug in the negative 1 and we get 4. We plug in the 2 and we get 4, which we already knew because we could see it on our graph. And then if we did the average rate of change function, we would just take 4 minus 4 in the numerator and negative 1 minus 2 in the denominator, and we get 0 again. So any way we go about it, the average rate of change on this one is 0 because it's a flat line, and so that is the line is 0. The rate of change is the slope and is 0. And our last example looks at a table. What is the average rate of change between negative 2 and 3? Well, negative 2, if we look at our table, here's negative 2, and 3 is here. And so, yes, it has these variations in the middle, but we don't really care about the variations. We basically just want the slope between these 2 points. And so the slope between these 2 points, we would calculate it just like we would calculate any other slope. We're just ignoring the fact that it has this inconsistent pattern in the middle because we don't care about that. We're just looking for the average rate of change. Negative 18.5 to negative 11 and 3 to negative 2. Just make sure you're staying in the same order as each other. So we get a negative 7.5 over a positive 5, because 3 minus negative 2 is 5. And if we divide that out, we get an answer of a negative 1.5. And so again, I don't know what units this is. I don't know what table this is. Maybe it's dollars per year. Maybe it's, I don't know. It could be anything, but the rate is average. The average rate is it's losing 1.5 every whatever, every second, every year, every day, whatever the case may be. Okay, that is the end of our average rate of change. I don't have space here for a summary, but you are welcome to write up your own summary if you would like. I'm not requiring it, but that might help. As always, if you have any questions, please write your questions down in the margin so that we can answer those in class tomorrow.